Okay guys, welcome to part 3 of lecture 4. Here we will try to use the energy method to calculate the force or the torque of electric origin. When we say force of electric origin, we mean that we only care about the force component created by electrical energy. So here is the a system, okay? So we have a voltage source with internal impedance, and it will supply the current through the coil, and that coil can move one part, okay? And this part can this part is attached to a mass, and it's on the other side of the mass is connected to something fixed here, okay, through a spring, okay. So we can have a model for that system like figure 4.11 4.18 here. So we have the only internal resistance of the coil will be combined into this R. So here we will say we have a lossless magnetic field, and using that magnetic field we can create the force that can move the mass around, and the displacement is x, okay. On the other side, we also have some force from the mechanical component or elements. So we have the spring with the stiffness k and the length L here, okay. So the idea is that we will try to find a way to calculate the force using just electrical and just electrical parameter, okay. So one thing you need to remember here is that the here the force always acts in the direction of positive x when we apply this method. Please remember that. So now let's call Wm is the stored energy, and by the energy conservation principle we see that when we put electrical energy in, okay, we get some mechanical energy out, and the difference will be the rate. The difference will be the change of the stored energy. And now when you differentiate that equation, you will get the rate of the change of stored energy would be the electrical power in minus the mechanical power out, okay. So because we call Wm is the stored energy, so this is the rate of change, okay. So this is the rate of change. So our input, electrical input here, remember we're looking at the field, the input of the field. We are not talking about the loss, we are talking about the magnetic field where we don't have any loss. And here would be the mechanical power, okay. And I would be d lambda, V would be d lambda by dt, and we have the rest here. And finally we can prove that dWm will be this expression. So it will be a two variable function. It will be the function of lambda and will be the function of x, okay. We can pick one electrical and one mechanical variable independently. Normally we pick lambda and x here, okay, because our coupling medium is conservative. The change in the stored energy when you go from A to B in the lambda x plane is independent of the path of integration, okay. So it means that we can do, let me see, okay, no picture here, I'll draw the picture later, okay, in the live session. But basically we can go in many ways, but there are two special paths. So path A, okay, we will go on the x-axis first. So x-axis from xa to xb, And here when we finish as xb, then we will go from lambda a to lambda b, where x is not moving at all. And on the first component we have a constant lambda, so this is a special path. On path 2 we can have a similar way. We can move along the lambda axis first. Okay, we move along the lambda axis first, so x will be fixed and lambda is moving, and then we will fix lambda as the final value and we move along the x-axis. Okay, so that's how we calculate the change of stored energy when we move from A to B. Both methods must give the same answer. However, if we have the initial flux linkage 0, which will be a general case, popular case for us, when we don't energize, when we don't put any current in the coil, then lambda initial lambda A would be 0. Then we have no force to start with, and in that case this one is better. Okay, this one is better. Okay, so you will see that here. So we will generalize the formula to calculate the stored energy here. If we can do this, okay, then we can find a way to calculate the force using it. So here how, okay, remember that we developed that the change of the stored energy will be I d lambda minus f e dx, and this Wm is a two variable function. It's a function of lambda and function of x. So when we calculate the differential of Wm, we see dWm. Okay, it's normally dWm by d lambda multiplied by d lambda. So this is the partial differentiation of Wm with respect to lambda multiplied by d lambda, and this is the partial differentiation of Wm with respect to x and dx. So you see here we have both of them. We have both this one correct and this one correct, with no constraint, no special condition about lambda or x. So it can only be satisfied if this one is equal this, and this one, this minus Fe equal this one. Okay, and therefore we will have this, the first one here move to this, and the second one here become this, and this is our formula here to calculate the force. If you want to calculate the torque, okay, you will replace the force here by the torque, and you will replace the displacement x here by the rotational angle lambda theta here. Okay, so this is the end of part 3.